Good morning, everybody. Coming to you from 2 a.m. here in the UK. So I apologize if I look a little sleepy. It's been quite a day. I was just mentioning before joining my talk. Well, first of all, I'm super excited to be here. Want to stress that. But I was just saying I actually had a 3-hour flight delay coming home today. So I'm actually presenting this talk from my parents' living room rather than actually in Oxford. But nonetheless, all I need is my laptop and the opportunity to talk about maths. So as the title of my talk suggests, I am going to be talking you through various examples of some of my favorite ways to use maths in creative ways. Let's say some of my favorite applications of maths and using it in creative ways. And the sort of idea when I was putting this talk together that I was thinking here was to hopefully inspire you to think of other ways that you can present maths to your students in a teaching context. I'm not really going to be focusing on a curriculum or anything like that. This is more just some interesting bits of maths that I really enjoy, that I incorporate in a lot of the talks that I do in schools, and just kind of the kinds of topics and the way that I try to approach those topics to try and really generate student interest in those areas. So I will be asking you to do some maths. I hope being at a maths conference, you were aware that this was going to be a request. So when we come to that point, I will make it very obvious that I would like suggestions from the answers. So if you put those in the chat, then they will be fed through to me. And I will also leave some time at the end for questions. So if you do have any questions, I think there's a separate questions box where you can put your questions, and they will also be fed through to me at the end as well. So I have a nice intro slide, which just kind of shows all the various amazing people and organizations that I happen to work with, but that was already covered in the intro, so I won't stay on this one for too long. But there's loads of stuff that I do that's all on my website, all freely available. So if you haven't checked that already, I would hopefully recommend having a look and seeing if there's any stuff there that you might find of use. So I'm going to start with a video of the research that I do. So my PhD was in an area of maths called fluid dynamics, and I was working on climate models and also trying to model the spread of pollution in the ocean. And I'm going to be talking about that one in just a moment. But this video was actually taken on board a ship when I was doing some field work. So about 5 or 6 years ago now. And we were sailing around the Southern Ocean, the ocean around Antarctica. And I'm here trying to record a video actually for my parents to show them what the ship was like on the outside of the ship. And some of you may have noticed the rather large storm cloud approaching the ship. I haven't noticed it yet in the video. You'll see the point when I notice like what's happening, and sort of, I think it's here actually now I start to run. So we were in the Southern Ocean because we were trying to collect samples, and we were trying to investigate and collect data about how the ocean was responding to the change in the climate. Now, the Southern Ocean is great for this because it's the least impacted by humans. So we can kind of see naturally how the ocean is responding. So we got lots of really good data. Now, the issue with the Southern Ocean is, first of all, it's quite far away from the UK. So it took us a long time to get down there. But also, it's the stormiest ocean on the planet. And this that you saw in the video there approaching, so that was a Force 11 storm. The scale only goes up to 12, and having been in now 2 Force 11s, I really don't want to see what a 12 looks like. So this was the first Force 11. The second one actually hit the ship during the night. So I was asleep in my bed. And I didn't realize that there was a storm until a wave hit the ship and actually tilted the ship so much that I was catapulted out of my bed, flew 2 meters across the room, and collided with the wall on the opposite side of my cabin. It was quite painful, but it's entirely my own fault because the beds on the ship were actually fitted with seat belts. They basically had safety harnesses in the beds. But I would like to think like most sensible people thought, well, I don't really need to wear a seatbelt in bed. turns out I did. So the moral of the story is if you ever find yourself in a bed that has a seatbelt, it's there for a reason. So I learned that one the hard way. So as I said, we were trying to collect this data to understand and try and apply it and use it in climate models and different things. And then the other aspect of my PhD research was looking at ocean pollution. So apologies for the image, first thing on Monday morning for you all. This isn't a real whale, is the first thing that I will say. It's actually an art installation, which is created by Greenpeace, but it is based on a real situation. So in the Philippines, there was a sperm whale that was found washed up on a beach a few years ago. And this whale had accidentally swallowed lots of plastic. It wasn't trying to eat plastic. It was just going about doing what whales do, and unfortunately was swallowing and digesting all this plastic, which ended up in its stomach and unfortunately killed the whale. Now, there's obviously a very sad message about this. And, at the time, this was quite it still is a very powerful image. And this was there to try and draw attention to the issue of plastic pollution in the ocean. I think there's a lot more awareness about this issue in general, sort of over the last 10 years, through the result of work of organizations like Greenpeace and other sort of documentaries and different things. Now, the opportunity to do some maths with this is to actually use some of the numbers, some of the data that relates to this whale. So the whale that was found, the sperm whale, so they have an average size of 42,000 kilograms is the average for a sperm whale. And this whale was found with, I believe it was 30 kilograms of plastic inside its stomach. So what I would like you to do is your first mathematical task of the talk is, if there is a whale, we find a whale with 30 kilograms of plastic inside its stomach, what would be the equivalent amount of plastic you or I would have to consume to be in the same position as the whale? So just to give you an example, we would need to know the weight of the human. Here, this is me, I weigh about 70 kilograms. So basically what we're trying to figure out is 30 kilograms of plastic in the stomach of the whale, how much plastic would that equate to, or would that be equivalent to for you or I? And just, I normally, hopefully I don't need to stress this, but I'm going to say it anyway. Do not try this at home. Do not actually eat this amount of plastic. But I would like you to hopefully do a quick back of the envelope calculation and feed through in the chat on what you think might be the approximate amount of plastic that one of us would have to consume to find ourselves in the same situation as this whale. So I'll give you 20 or 30 seconds to have a little think about that, and then I'll show you the calculation that I did. And then we're going to have some fun with units, which I'll talk about in just a moment. So as I say, if you're taking part in this, and hopefully you all are, then just put some answers in the chat, put some thoughts in there, and hopefully they will be fed through to me, and then I can show you what I got, and we can see whether we agree or disagree on the amount of plastic being consumed.
We've got some answers coming in, Tom. 0.05 kilograms, 46 grams, 50 grams, 57
nice.
Grams.
Okay, so I'm guessing, very good. So I'm thank you, everyone. I'm guessing those range there is probably perhaps you're using your own body weight, which is obviously, of course, completely valid. I just gave the example of myself as 70. And also the 70 actually helps with the numbers, right? So the equation we're trying to do is we have the ratio or the proportion of plastic to body mass for the whale is 30 over 42,000. And importantly, they are the same units. And what we want to know is what is the unknown amount of plastic X versus the body weight. So here, the example of me of 70 kilos. So we can just multiply both sides by 70, and then you get 70 times 30, which has the nice 2100. And so it cancels really nicely with the 42,000. And so we're going to get 0.05 kilograms, which is about 50 grams, which sounds exactly like what a lot of you are saying. So very well done, everybody, for doing your first bit of maths this morning, possibly. Now, final further step, and this is something I like to do a lot at whatever talk I'm doing or level I'm teaching students, is to play around with units. So we've got 50 grams of plastic, but that is quite hard to picture. It's, you know, I think I have a rough idea how much plastic that is, but it's sort of, I don't know, it doesn't quite feel like relatable just in that sort of number. So as a final little exercise, I would like you to all see if you can figure out, and I'm not going to tell you the weight of a plastic bag, but how many plastic bags would that be equivalent to? So again, definitely do not try this at home, but if we were to try and consume 50 grams of plastic, approximately how many plastic carrier bags would that be equal to? And I find this in particular seems to be quite a powerful image or a powerful figure when I'm explaining this one to students as to the sort of the poor whale and the situation that it found itself in. So how many 50 grams of plastic, approximately how many plastic carrier bags would that be equal to? And again, if you have any estimates or ideas, do pop them in the chat. So the figures that I have used here, so I believe a plastic carrier bag is around 7 grams or so. So this, of course, is approximately 7 plastic carrier bags. And as I say, I think that sounds pretty awful, as you could imagine, to sort of think to accidentally consume 7 plastic carrier bags, just sort of going about your daily business completely by accident. And I think that kind of image, first of all, it's a nice opportunity to talk about ratios and different things, but I think sort of there's an important message there as well about when presenting data and presenting it in a way that's most relatable to the audience that you're trying to inform about the situation. 7 plastic carrier bags certainly to me sounds a lot worse than 50 grams of plastic. Now, I couldn't resist doing some naming and shaming whenever I talk about plastic pollution. With, of course, as I say, with this being one of the main areas of research that I work in, trying to understand the spread of plastic pollution around the ocean. So I'm going to look at the top 3 worst polluters, and this is by the river in that particular country. And I'm going to give you the daily amount of plastic that's found in that river or dumped into the ocean from that river. And what we're going to do is actually, I'm going to present it again using slightly different units that, again, just to kind of play around a little bit with the numbers and also to make it a little bit more relatable to what's happening. So before I reveal the 3, I'm sure you're all probably forming guesses or ideas in your head. Again, if you wish to share them, please do feel free to take part in that discussion. So in 3rd place, we have the Cross River in Nigeria, where 126 tons of plastic per day is deposited into the ocean. Now, as I said, we're going to have some fun with units. And what we're going to do here is actually represent this in terms of number of elephants. And the average weight of an elephant is 4 tons. And so just from this single river in Nigeria, approximately 28 elephants worth of plastic, which is this number of elephants on the screen, enters the ocean every day. Now, this is only the 3rd worst. So we've got 28 elephants from the Cross River in Nigeria. In 2nd place, we have the Ganges River in India, which is 316 tons of plastic per day. And again, if we divide that by 4, we can get the number of elephants equivalent, which is 79 elephants, which looks like this, which is a lot of elephants. And again, that's in a single day, and that's just plastic pollution. We're not accounting for chemical pollution or anything else. This is just plastic. And again, the number one, which I'm guessing possibly quite a few of you may have thought or may have come up with yourselves, is going to be the Yangtze River in China, which is 912 tons of plastic per day that leaves that river and enters the ocean. So again, if we convert this to our units of elephants, it's 228 elephants worth of plastic in a single day. So that looks like there's one lot, there's two lots, there's three lots, almost 3 times as much as we saw from the second worst river with the river Ganges. So again, like this is just one way that I sort of like share and talk about my research and sort of try and get across the message around plastic pollution, around pollution in the ocean in general, and also sort of use it as an opportunity to talk about units and also data presentation, again, to try and appeal to the audience and the person you're trying to explain that particular message to. So moving from sort of the environment and my actual research, I'm now going to talk about some of the other things that I enjoy, and again how I sort of can use maths in those contexts to try and interest and engage students. So we're going to talk about video games, and we're going to talk about Pokemon. So I'm a very big Pokemon fan. I have lots of Pokemon tattoos, and I do still play Pokemon. I was playing it on my flight I was on earlier today, in fact. So there is a dragon Pokemon shown on screen called Charizard, one of the original Pokemon. And I was asked a question, I think it was actually by one of my students, just a sort of like a joke question a while ago, which was sort of saying, if we suppose that Charizard was a real creature, so we have a fire-breathing dragon style creature, then how many calories per day would that creature consume? And now I think that's a fantastic question for so many reasons, but it really kind of like appealed to my imagination, not only as a Pokemon fan, but also the opportunity to do, to work with numbers, to do some mathematical calculations. And also the fact that we're talking about fire and sort of it brings in like elements of physics and chemistry. There's just like so many different ways you can explore this particular question. So this is how I thought about the answer. So I thought to start with, we kind of need to know the size of this creature. So this data does exist. Pokemon is very big. You can look these things up online. So the average size of your creature, of your Charizard, is about 1.7 meters tall, and the weight apparently is around 90 kilograms. So again, of course, this is a fictional creature, but it is about the size of sort of an average male human, shall we say, approximately. And so if we go off like the standard, let's say, recommended daily allowance of calories for an average size male human, that gives you approximately 2,500 calories worth of food just to exist as a creature of that size. Sort of, let's call that a lower bound, but it's a ballpark figure. Now, the other interesting question with this then is, well, what about the fire? Because, there's, as you can see in the picture, even if you know nothing about Pokemon, you can see in the picture that this creature has a flame on its tail. And if you actually read about the description of the creature, that the fire is always burning, because if it is extinguished, then the creature has died. That's kind of one of the sort of legends around the Pokemon, one of the folklore like stories. So you think, well, okay, so in order to have this burning flame on the tail of this creature, then you're going to need more energy as well. So we need to talk about the fire triangle. And this is what I meant by the opportunities kind of bring in sort of like some physics and chemistry into the problem. So we need oxygen, we need heat, and we need fuel. So the oxygen, well, that's going to come from the air. There's oxygen in the air. That's why we have fire. Fires exist on Earth, things burn. So we've got the oxygen aspect. The heat, well, let's just suppose that comes from the body. We've already kind of accounted for the sort of general existence of the body for the food and different things. So then that just leaves the fuel. So we're going to need some additional amount of calories, some additional amount of energy in order to supply the fuel. And then this is where there's potentially different ways of modeling this, but I thought about sort of saying, well, let's suppose the flame, and of course, again, this is an opportunity to explore modeling and assumptions that can be made when answering these kinds of questions. But I sort of thought, well, let's suppose the flame is a Bunsen burner. So let's take a typical Bunsen burner, which most students will be familiar with in chemistry science class. So take a typical Bunsen burner. So approximately 1 kilowatt of energy per hour is required to have a sort of average sized Bunsen burner flame. So we need to convert that into calories. So again, this is another exercise in units. So a calorie is 0.00162 kilowatt hours. So if we need the flame to burn for 24 hours, then we need 24 kilowatt hours of energy. And so that's actually going to be 24 divided by 0.00162. So that's about 15,000 calories. So in order to answer the original question of how many, if this fictional dragon-like creature Charizard were to exist, how many calories would it need if I had a pet Charizard? It would be about, I think it's going to be 15,000, 17, 18, maybe like 6 or 7 times the amount of food that a human would require. So in other words, quite a lot, I think, would be the conclusion to draw there. And I've used this kind of like exercise and question and similar ones around it. Had a lot of fun getting students to think about answering this question. Sometimes with prompts and guidance required to kind of point them in a particular direction. But other times just sort of saying, here's the question, think about how you might try and answer this and see what answers they come up with. And of course, there isn't really a right or wrong answer, in particular because it's a fictional creature, but it does give an opportunity to discuss good and bad assumptions within mathematical modeling. Okay, now we're going to completely shift gear, shift focus, and we're going to talk about possibly my favorite thing outside of maths, which is going to be football. So I've got a little video that I'd just like to share with everyone. So sort of a throwback to pre-COVID times, which I'm sure we're all very fond of. And this was the World Cup in 2018. And I've got a little clip of the England men's football team in a penalty shootout.
Eric Dyer places the ball on the spot. And England win on penalties!
So as you can see, this is quite a big deal for us England fans, because this was the first time in 22 years that the England men's football team had actually won in a penalty shootout. So that was Eric Dyer who scored the winning penalty against Colombia in, I think it was the round of 16 in the 2018 World Cup. Now, one of the reasons perhaps that, so I did a little bit of investigating, let's put it that way, being a football fan and being a mathematician. And I found that one of the reasons perhaps that you could be attributed to why the England team kept losing penalties was they were generally taking quite bad penalties. And what I mean by bad penalties is they were aiming for areas of the goal where they had quite a low probability of scoring. So, but fortunately, they didn't do this against Colombia. So this is an opportunity to bring in some probability, some statistics, and also possibly my favorite ever application of some very common bits of maths that I certainly recall from when I learned them, like the kinds of maths that students don't ever realize have any use outside of the classroom. So the starting point of this is to look at, it was actually a study done by the University of Bath and a guy called Ken Bray. And it looked at trying to model and trying to map what they called the unsavable zone in a football goal. So you've got there in gray, you can see the rectangle that is the goal. And then they actually recorded a video of professional goalkeepers trying to save penalties. And they recorded the average reach of that goalkeeper. So you can think of this from like a physics perspective. So what is the physical limitation of a human standing in the center of a goal, trying to dive and reach a football? So when the ball is kicked, from the penalty spot, so it's 12 yards away from the goal. When the ball is kicked, you have approximately 0.5 or half a second to actually react and try and save the ball before it goes into the net. So the question is just, how far can a relatively athletic human move in half a second? And the average was this red line. So this was called the diving range. And the area outside of the diving range that is still within the goalposts, that is what was called the unsavable zone. And so kind of from the physical perspective, you're saying, well, clearly it feels like it should be better to aim for the unsavable zone, aim outside of the diving range. And then if you actually look at the data, this was completely backed up. So they looked at, I think it was 3,000 different penalty shootouts. It was an insane amount of footage of people taking penalties. And basically they found that if the player aimed inside the diving range, so if they aim inside the red semicircle, probability of scoring was 0.5. So approximately 50% of the penalties where the ball was positioned and aimed inside the red semicircle, inside the diving range, 50% would be successful, they would be goals, and 50% would be either saved or potentially go over the crossbar. Because as you can see, the red does go just a little bit above the top of the goal in the center. And then if you aim outside of the diving range, and of course, outside of the red semicircle includes missing the goal. So you could be aiming left, you could be aiming right, you could be aiming above the goal. So even though there's a much larger opportunity to miss, it's potentially a much more difficult shot, the probability of success actually goes up significantly to 0.8, giving you an 80% chance of success in this region. So just from sort of the physics is telling you should be aiming in this unsavable zone, and then the data of this actually happening is also supporting what the conclusions were drawn from the videos and from those sort of experiments. So, of course, being a mathematician, I thought, well, this is all great, but I kind of want to go a step further with this because what we've really got here is a geometry problem. So we have a rectangle, which is going to represent our goal. So we have a height of the goal, which I've labeled B on the right-hand side there in green. And we know that value. So there's a standard height. Every goal is a standard height. There is also a width of this rectangle. Now, I decided, just for ease of notation, to actually label the total width is going to be 2A. So half of the width is therefore going to be A. Again, as shown in the diagram. And then we have the diving range, which we've just talked about from the experiments. So again, we also know the value of this radius R, capital R, because this is a semicircle. So it's a semicircle centered on the middle of the goal. And we know that radius to be this uppercase R. So what we really want to do now is figure out, well, where should we aim? Where should a footballer, where should they aim their shot such that they maximize their chance of scoring, but also like allowing for a little bit of error? So if there was no, if there was like a 0.1% error in the shot, you would say clearly aim for the very top corner, because if you can hit any single point you want, that is clearly furthest away from the goalkeeper and inside the goal. Now, of course, even the world's best players cannot hit like the head of a pin. So there's always going to be some error. So really, you want to actually have almost like a circle around your ideal shot. And you want that circle to be as large as possible, such that it still is safely inside the goalposts and it's safely away from the goalkeeper. So you want to keep away from like these three things. You want to keep away from the crossbar at the top, the post at the side, and the goalkeeper, or this diving range in blue. So really, you want to fit a circle perfectly into that gap, which is shown there in purple. So, and this is the point where if you have zero interest in football or have no idea what I've been talking about up to this point, now it is just a maths problem. It's just a pure geometry problem. And what we want to know is, can we work out the location of the center of this purple circle? So can we work out the value of lowercase r? Now, I'll give you all maybe, let's say, like a minute or so to think about this. And just, again, I haven't told you any numbers yet, so I'm not expecting anyone to give an answer. But maybe if you want to just sort of jot down any thoughts you have, if you want to share anything in the chat about potential ways you could go about trying to solve this, like what are your first thoughts when presented with this problem? So we're trying to find the center of the purple circle with the value of the lowercase r, the radius. Because if we know the value of the radius, then we know to go that far inside of the post and also that distance below the crossbar. And that would be the perfect place to aim your penalty, allowing for this error in the particular shot. So as I say, I'll give you a little bit of time to have a think. Please do pop some stuff in the chat, and then I will go through in just a moment sort of the way that I would try to solve this problem. And it does involve two very, very famous and very important pieces of maths that lots of students don't realize are so applicable, which is why I particularly enjoy talking about this problem, and also being a football fan.
Okay, Tom, Amun has asked us, would A be equal to capital R plus 2 little r?
Would A be equal to capital R plus 2 little r? I don't think A would. No, I'm not sure if there is an exact relation there between those two. Not that I know off the top of my head. No, I don't think so. But we definitely want to try and get a relation involving A, capital R, and little r. So I can give you all, it's hopefully going to be a nice clue, which is to draw this line. So this is going from the center of the goal, and it's passing through and it's going to the center of our circle that we're trying to work out the location of. And of course, because of the way we have positioned the purple circle, it's actually tangential. It perfectly touches the blue semicircle. So we know that that distance from the center of the goal to the center of our circle is capital R plus our unknown value of lowercase r. So now we have the diagonal line. We can also add a perpendicular, like so. So if we drop this perpendicular down to form a right angle with the ground, with the base of our goal, we know the total height is b. So therefore, the remaining height is b minus r, because we are the distance r away from the post at the top, crossbar. And then we can complete the triangle, because the bottom, the total distance along the bottom there, well, from the center to the post, the total distance is a, but again, we are a single radius inside of the post, so we get a minus r. So ultimately, it just comes down to quite possibly the most famous theorem that I remember from school, Pythagoras' theorem. So a minus r squared plus b minus r squared is equal to lowercase r plus capital R squared. So we can use the right angle triangle, Pythagoras' theorem there, to get now an equation for the unknown value, lowercase r. So if I expand those brackets, and we can tidy those terms up. So of course, the important thing here is to group the terms according to powers of lowercase r. So that's what I've done here. So we've got an r squared term. We've then got a linear term with just a single r term. And then we've got those constants at the end. So if I now give you the values for these various things, the numbers are horrible, which is why I use symbols to start with. So the width, half of the width is 3.66 meters, the height is 2.44 meters, and the diving range is 2.86 meters. So when we substitute those in, the equation is very, very close to this. R squared minus 18r plus 11 is equal to 0. So now we are trying to find this unknown value, the radius of this circle where we want to aim our shot. And now all we have to do is solve a quadratic equation in order to get that solution. So this is the second really important sort of famous bit of maths, the school maths that comes in here, which is solving quadratic equations. I never grow tired of the expressions on the students' faces when they finally sort of see this and realize that these, they know how to solve a quadratic equation, and they can now use it to figure out where to aim their penalty kick next time they're playing football. So you do need to use the quadratic equation to solve this. It doesn't factorize very nicely, but you can do this. And one of the solutions you get is very negative. And of course, that's an interesting discussion in itself about why do we ignore that one. And then the one that we want is 0.65 meters. So to answer the original question of where is the perfect place to aim a penalty when taking a penalty kick, it is 0.65 meters inside of the post and 1.79 meters above the ground. So it's the easiest way I remember this, and I have used this because I do still play football, and when we're doing this in training sessions, is you get somebody to stand. If they put their hand on the post, sort of just inside the goalpost, then you want to basically try and aim for their head when you're taking your penalty. And that is approximately equal to the center of this circle. But I just love the fact that I had no idea this was going to turn out this way when I first started looking at this problem. I just love the fact that it sort of is an application of Pythagoras' theorem and quadratic formulas, which are two really, really important bits of maths that can often feel like to students, at least in my experience, that they're just doing it for the sake of it, or they're doing it for exams. And I think this is a really nice problem that shows the usefulness and how those things can be applied in a situation that might potentially grab their attention a little bit more. Now, sticking with geometry, so this is the fourth topic of 5. So I often talk about my favorite shapes when I'm doing talks with school kids and different things. And we're going to start by defining the rules of my shapes, my favorite shapes. So there are 3 very simple rules in order to be classified as one of my favorite shapes. You need to be 3-dimensional. So that's our starting point. It must be a 3-dimensional shape. So, a sphere versus a circle, a cube versus a square. We want the 3-dimensional version. Every face of my shape has to be the same. So if one of the faces is a triangle, then all of them will be triangles. If one of them is a hexagon, then all of them will be hexagons, etc. And they're all regular. So for a triangle, it would be an equilateral triangle. For a 4-sided shape, it would be a square, as opposed to a rectangle. And then the third rule, the same number of faces must meet at each corner. So the easiest one to think of there, or the easiest example I can give you, is perhaps the cube, which I've already mentioned. So a cube is actually one of my favorite shapes. It is a 3-dimensional shape. Every face is a square, so every face is the same regular shape. And if you think about the corner of a cube, you've actually got 3 faces all joined together at every corner. So basically that makes it very symmetrical. That's what that third rule is doing. It's helping to make things really symmetrical for these particular shapes. So a cube is one example. There are, in fact, believe it or not, only 5 shapes that satisfy these 3 simple rules, which I even now find quite amazing. And I know how to prove this, but I still find it quite amazing because the rules themselves sound so general. It feels like there should possibly be an infinite number of shapes that satisfy these rules, but you can in fact show by considering angles and counting the total angle at a corner is how you do it. You can actually show there are only 5. So does anyone, I've given you the cube, does anyone know the name of any of these other shapes or want to describe any of these other shapes that satisfy these 3 simple rules? And they're going to appear on my screen in a certain order. So maybe we'll see if we can get a few answers first. But the cube is the second one, which is why otherwise I'd show you that one. So any other shapes, I'm looking for something that's 3-dimensional. Every face is the same. And I want the same number of faces to meet at each corner.
Yes, so some answers coming in now, Tom. Platonic solids, icosahedron, 20-sided die, 4-sided, and 8-sided.
Yeah, nice. Yeah. So somebody spotted that my favorite shapes are the Platonic solids. Very good. Yeah, that is their name, and I'm going to tell you the story behind that name in just a moment. Yeah, and I heard lots of very sensible answers, lots of great names there. So tetrahedron is going to be the one with the fewest number of sides, or a triangle-based pyramid, as lots of students seem to refer to it. So again, it's 3D. Every face is a triangle, and every corner you've got 3 triangles joined together there. You've got the cube, which is the sort of perhaps most common one. So again, 6 squares, and you've got 3 joining every corner. I heard someone say 8-sided, I think came through. So that's an octahedron, where every face is a triangle. And you've got at every corner, you've got 4 faces meeting there. Then we've got the dodecahedron. Well done if you got that one, which is a 12-sided solid where every face is a pentagon. And then finally, the 20-sided die, or the icosahedron, to give it its full title. So that was another one made from triangles. Now, I'll very quickly, just because I mentioned it, the way you prove this is by counting the total angle at each corner. So if you think about a triangle, you have 60 degrees in an equilateral triangle at each corner. So if you have 3 of them joining together, which is the minimum number required to be 3-dimensional, you have 2 triangles joined together at a corner, then it would actually be a flat shape. It takes a little while perhaps to, normally I have little models I'd show you, but they're down in Oxford. Don't have them with me, unfortunately. But if you have 2 shapes and stick them together, like it's 2D. So you need at least 3 joining at a corner to satisfy rule number 1. So you put 3 triangles together at every corner, and you get the tetrahedron. And then you say, okay, well, what if I put 4 triangles at every corner? That's the octahedron. What if I put 5 triangles at every corner? That's the icosahedron, the 20-sided one. What if I have 6 triangles at every corner? Well, the total angle, if you have 6 triangles, is 6 times 60 is 360 degrees. So if your total angle at the corner is 360 degrees, it's actually flat. It's become flat again. So you've lost that 3-dimensionality. So ultimately, you need a total angle that has at least 3 shapes at a corner, and the total angle has to be strictly less than 360, because it can't go above that, because then you can't fit more in. And if it's exactly 360, it's flat. So you can't build any more from triangles. We've got 3, 4, and 5, which are the tetrahedron, octahedron, and icosahedron. So the next simplest shape is a square. 3 squares gives you a total of 270 degrees. That's the cube. If I add a 4th square, I've got 360. It's flat. So the only one from squares is the cube. Let's go the next shape up, the pentagon. I think it's 108 degrees, the angle in a pentagon. So minimum is 3 of them. that's 324 degrees. So that's fine. And you get the dodecahedron, 12 sides. But then if you try and add a fourth pentagon, you can't fit it in. So there's no more you can do from pentagons. And then if you went to a hexagon, the angle of a hexagon is 120. So if you have 3 of them, then you get 360 and it's flat. And then if you went to 7-sided, 8-sided shapes, 3 of them is always going to be more than 360-degree angle. So this was actually done by a chap called Theaetetus, I believe his name was, like 3,000 years ago, this proof. It's very clever just by counting the angles and the numbers of shapes joined at each corner. Now, you may, as was mentioned in the chat, have noticed that these are called the Platonic solids. They are not named after Theaetetus. They are not called the Theaetetan solids. And that's basically because Plato got wind of this and heard what Theaetetus had been doing. And he sort of, being Plato, thought about this and decided that he couldn't believe that there were just 5 shapes that followed these rules. And of course, they're all very symmetrical and they're all sort of very nice for us to look at. And so Plato came up with this theory that the shapes themselves must play a higher role in the universe. So in the time of the ancient Greeks, they believed that the whole universe was made from 4 elements. So you have fire, you have earth, and by earth, we mean the ground, not the planet. Important to stress that. We have water and we have air. Now, there are 4 elements and we have 5 solids. So this was possibly the first clue that Plato wasn't really onto something, but being Plato, he was completely undeterred and so decided to invent or create a 5th element called the heavens. So now his theory was we have 5 elements that make up the universe, and there are 5 of these solids, and he felt that they were so important that it must be connected. And so he decided to argue that each one of these elements must be made of smaller pieces, where those smaller pieces are one of the now known Platonic solids. So what I would like you to all do, and this is always a fun exercise, is to put yourselves into the mind of Plato. So again, think back 3,000 years, you are Plato, you have this incredible theory that the 5 elements, earth, fire, water, air, and the heavens, each one of them is made from small pieces. And each one of those pieces is one of these shapes. So, and there is some logical sense to this. But I would like you to match up which shape goes with which element. And if you want to add a reason, then please do. It's always very entertaining to hear the reasons. I'll give you a couple of minutes to think about this. Again, obviously, you can very well can just do this to yourself, but if you'd like to share your answers, that's also brilliant. And we can see how many of you are able to put yourselves into the mind of Plato and answer this question. So which shape do you think is matched with which element? And I will give you the answers according to Plato and talk you through his thought process and reasoning behind it. Because a lot of them make sense. Not all of them make sense, but a lot of them do actually, I think, have some logic behind them. And I also like to point out again at this point, obviously, again, I don't want to patronize you all, but it's always worth saying, obviously none of this is actually true. However, as much as I enjoy laughing at this kind of concept and this idea, Plato was actually not that far away from, something that took us almost 3,000 years to figure out, right? This idea that everything in the universe was made from small pieces, right? Atoms, molecules. We've got there now. So he wasn't a million miles away with what seems like such a radical idea. Just, they had the wrong elements in the first place, I guess. So have we got any suggestions coming through so far? And if there's any for Earth, maybe it's good to start there, because the first arrow that will appear will be the one for Earth.
No, it's all pretty quiet so far, Tom. So
maybe this is the non-maths question, right? This is the having to think carefully about what's happening. So okay, so as I say, I'm going to do these in the order as they're shown. So the first one, again, according to Plato, is Earth, and that is going to actually be the cube. Now, the reason he gave for this was that the cube is a very strong and sort of stable structure, which allows you to build things. Because, of course, thousands of years ago, the earth itself, the dirt soil, was used to make construction. It was a very prominent feature of construction. And so Plato's reasoning was that if you were trying to stack these things together, which would provide a very strong and stable base, it would be the cube. Now, for the next one, fire is going to be the tetrahedron. Now, again, I think this one sort of makes some kind of logical sense. So Plato here said, well, fire is sharp to the touch, it's painful to the touch. And so therefore it should be represented or built from the sharpest solid, the sharpest shape. So when we say the sharpest, what that means is going to be the shape that has the smallest angle at a particular corner. So that would be the tetrahedron. Each angle there is 3 lots of 60, so it's 180 degrees. So fire is going to go with the tetrahedron. The next one, water. So water is going to be the 20-sided icosahedron. And this is sort of similar reasoning to fire, because like fire was sharp to the touch and therefore should be the spikiest of our shapes, water flows. Water kind of rolls off your hands. And so therefore, again, according to Plato, it should be the roundest or the smoothest shape. So what that's going to mean here is the one with the sort of most sort of numbers of sides is basically the one that's going to be most like a sphere. So water is therefore going to be the icosahedron. Then that just leaves the remaining 2, which are possibly the hardest 2 to place. And Plato didn't really have any reasons for these. So air, he associated with the octahedron, and then heavens leaves heavens to be associated with the dodecahedron. Now, it has since been pointed out to me, and again, this is not what Plato said, but he certainly missed a trick here, because with having invented the heavens as this additional element, the ancient Greeks believed in the gods of Olympus, and there were 12 gods that lived on Olympus. So the 12-sided dodecahedron makes a very convincing argument to be matched with the heavens. But again, that was not Plato's reasoning. That was actually pointed out to me by a student a few years ago. But I think that one, because then if you match that one up, then you can just, by process of elimination, argue that air has to be the octahedron. Okay, so I think, so as I say, these are actually my favorite shapes. I do have these tattooed on my leg. It's one of my many maths tattoos. But I do find that this particular topic and like the story and the history behind the discussion around the shapes really gets sort of the imagination of the students. And I find that they do really enjoy, this particular matching exercise, and sort of, it gives you telling the story behind the name and the proof and the counting of the angles. I think it just, like, the history behind it all just really helps to bring it to life as a topic. Now, the final thing I would like to talk about is an example of some mathematical modeling. And again, it comes from a question that I was actually asked. This was on my YouTube channel. In fact, it was a comment on one of my YouTube videos, one of the first ones I made a while ago now, which was just someone asking the question, how many ping pong balls would it take to raise the Titanic from the ocean floor? And this to me is, I just think it's such a brilliant question, because I don't know why, and I can't explain it, but as soon as I read this question, I had to know the answer. Not because I felt like it was completely useful information or was going to, have some big impact on my life and what I do or anything. I don't know, it just got my curiosity. I was like, I need to know the answer to this question. And it is actually based on a real theory, a real suggestion that was put forwards in, I believe, about the 1970s, I want to say. So just after the Titanic wreckage had been found. So the Titanic, for those of you who don't know, very big famous ship, the largest one ever built at the time, that set sail from Southampton in the UK to the US, and it sank just off the coast of Canada, in fact, from hitting an iceberg. I think it was 1912, if memory serves me correctly. And the wreckage was found, I think it was in the 1970s. And so there was a big kind of like call and a big scramble for ideas around what they should do with the wreckage. Can they bring it back to the surface? And this was a real theory put forwards by a group of scientists, which in itself is very entertaining, because we'll come to that later. We'll answer the question. And then if any of you want to think about why would this not work in practice? Because theoretically it would work. And I will hopefully convince you why, and we'll do the calculation. But if anyone would like to offer any suggestions as to why it would not actually work in the real world, then that's something to think about. So the idea of this is, again, it's just a great modeling question to try and think about, well, what do we need to know to answer this? And what kind of like physical theory or maths equations do we need to use to be able to answer this question? So the key thing we need here is actually Archimedes Principle. So Archimedes Principle tells you how to calculate the buoyancy force on an object. So the idea is, if you have a ping pong ball, spherical object, ping pong ball, you have weight pulling that object down. So imagine your object is submerged in water. It has a weight, which is gravity times its mass, and that's pulling it down. Now, there's also a force pushing upwards, which is the buoyancy. That's much more difficult to calculate. And Archimedes' principle tells us how to calculate the buoyancy. And basically what it says, as it says there, equals the weight of the fluid displaced by the object. So what you have to do is you need to calculate the volume of your object. That's the first thing you need to know. And there's a lot of interesting exercises and fun to be had here in looking at different shaped objects, but we're just looking at spheres. So you need to know the volume of your object. Okay, so it says the buoyancy force acting on a submerged object is equal to the weight of the fluid displaced by the object. So we need to know the density of your fluid. So if we know the volume of our object, then you multiply the volume by the fluid, and that gives you exactly the weight of the fluid that's been displaced by that object. So your total force, either upwards or downwards, is weight minus buoyancy, or buoyancy minus weight. So that's basically how you do it. So total force is buoyancy minus weight. So if your total force is positive, then your object is going to float. If your total force is negative, that means the weight is larger than the buoyancy, and therefore it's going to sink. So how do we apply this to the Titanic and ping pong balls? Well, we need to work out the buoyancy force of a single ping pong ball, and then work out how many of those we need to be able to have enough buoyancy to lift the Titanic. So the first thing, the Titanic weighs 47.5 million kilograms. We need to know the weight of the thing that we're trying to lift. It's a good place to start. Again, we now need to apply Archimedes' principle. So we need to know the buoyancy force, or the total force, on a ping pong ball. And in order to calculate that, we need to know the volume of a ping pong ball and the weight of a ping pong ball. So we need to know some properties around a ping pong ball. So a standard ping pong ball has a 2 centimeter radius and it weighs 2.7 grams. Okay, so we've got 2.7 pulling it down. That's our weight. So we now need to know its volume. So the volume is 4 thirds pi times the radius cubed. The radius here is 2 centimeters, so it gives us a volume of 33.5 centimeters cubed. So now we know the volume of our object, so that's the amount of fluid displaced. But we need to know the weight of the fluid displaced. So that means we need to know the density of our fluid. The Titanic is in the Atlantic Ocean. So the Atlantic Ocean density is 1.027 grams per centimeter cubed. So therefore, the total sort of force equivalent acting upwards is going to be 33.5 times 1.027, 34.4 grams. Now remember, we need the total force. So we have 2.7 pulling downwards. We have 34.4 pushing upwards. So the total force is 31.7 grams. Now, the final step, and I mentioned this right at the start of the talk, we've come full circle, is we need to look at the units because we need to be able to compare things with the same units. So we need to turn 47.5 million kilograms into grams. So it's 4.75 times 10 to the 10. And then we just simply divide that by 31.7 to give us the final answer of 1.498 billion ping pong balls required to lift the Titanic to the ocean surface. Now, as I absolutely love the answer to this question, I love this question, but I since discovered an even better thing about this question, about this calculation. So, of course, 2 weeks ago now, it was Pi Day, March the 14th, now known as the International Day of Mathematics. And a challenge I set my students every year is to come up with their own unique definition of pi. So, of course, we can have the standard ones, pi is 3.14, or pi is 22/7, or if you're an engineer, pi is 3, or what's the other classic? Or its proper definition, pi is the circumference divided by the diameter. Now, the fun to be had in this is, or at least I think, is any calculation that you do, any equation that you do that happens to involve pi in some context, which basically means anything involving circles or spheres, you can actually rearrange that equation to get a definition of pi. Now, you'll notice on screen that we had to use pi in this calculation because we used the formula for the volume of a sphere. It was 4/3 pi times the radius cubed. So what I can do is take this calculation and rearrange the equation to get a formula for pi. And this is still, I think to this day, the best definition of pi I have ever seen. Pi is equal to 3 times the weight of the Titanic divided by 4 times the number of ping pong balls required to lift the Titanic times the density of the Atlantic Ocean times the weight of a ping pong ball times the radius of a ping pong ball cubed. And with that, I will end my talk, and I am more than happy to take any questions, or if anyone has anything they want to discuss, or if anyone's figured out why we couldn't actually lift the Titanic with 1.5 billion ping pong balls, then I would love to hear from you. But it's been a great pleasure. I hope you've enjoyed it, and I am more than happy to take any questions in the remaining 5 to 10 minutes or so that we have.
Thank you, Tom. That was fantastic. It's I'll funnel you through some questions if people have them as they come in.
Awesome. And I'm still awake.
Well done.
I just looked down at my phone and was like, it's 3:05. What is going on?
There's a few people who are worried about the idea of putting another 1.5 billion ping pong balls of plastic in the ocean.
That's a very good point. Yeah. Yeah, we definitely shouldn't do this for many, many reasons. But I just love the fact that it was put forward as a real theory. I think it shows creativity, but also like a kind of a lack of actual critical thinking around the problem. Another great one, it's a bit of a rabbit hole if anyone wants to go down this, but there were lots of other suggestions put forward from actual scientists around how should we think about trying to lift the Titanic. So one of them was to pump the ship full of Vaseline, which would then make it buoyant. But my absolute favorite was if you could somehow basically pump liquid nitrogen into the Titanic, it would then actually freeze and basically become itself a giant iceberg that would then almost like poetically float back to the surface. It was taken down by an iceberg, but if we could somehow freeze it with liquid nitrogen, it would then float back to the surface as an iceberg. So I think that's the most poetic of all of the suggestions. Obviously, none of these would actually be even remotely worth the money, but theoretically, potentially could work.
There's a lot of people who are saying, Tom, that they're going to check out your website for more great ideas. So that's great feedback.
Awesome, thank you. Yeah, as I said, this was kind of I don't know what people were expecting, but I just sort of, when I was thinking about what to talk about, I just figured I would try and take some of my favorite examples of just, and hopefully it's just got all of you thinking and got those creative juices flowing about ways of just introducing maths into other topics, ways of taking things that your students are interested in and then trying to figure out, how can I bring maths into that topic? How can I talk about their favorite video game, the maths behind it? How can I, for me, bring maths to football and sport and different things?
Yeah, there's a few people who've said that they like the environmental focus of the problem set because it obviously resonates with a lot of students.
Yeah, definitely.
Oscar has asked, can you share some of your findings of your research about climate change affecting the Southern Ocean?
Yeah, so we were looking at a very, very specific feature in the ocean, which are called sub-mesoscales. It's a particular sort of size feature on the scale of like a kilometer. And the main thing that we were looking at within that project was current. So when you're running a climate model, you have to decide on the resolution of your model. So basically you divide up the ocean and the atmosphere, you divide it up, like the whole world, up into a grid. And, ideally you want to make it as pixelated as possible, because then you get really, really accurate information and really, really accurate predictions, and you can model each individual pixel. But then you just need an astronomical amount of computational power, and it will take like 10 years to run. So there's a trade-off between we want to be able to generate results, because if you run something for 10 years and realize that one parameter was a tiny bit off, you've got to wait another 10 years to do it again. So there's a definite trade-off between the resolution of the model and how like usable it actually is. And what we were looking at in this particular project, we were basically saying that there's a really important feature, these sub-mesoscale features, that only occur around the 1 kilometer length scale. So we were basically saying you need to run these simulations at the 1 kilometer scale for each grid square, whereas at the moment they tend to be run at around the 10 kilometer grid square. So we had done lots of simulations showing that if we couldn't do the whole Earth, but we did just patches of the Southern Ocean. We ran the simulations and got like predictions of what was happening based on this 1 kilometer scale. And then our idea was to go to the Southern Ocean, collect all of these samples, and show that the data we got there from the real measurements was much, much closer to our 1 kilometer scale predictions than what you're seeing from the 10 kilometer scale predictions. So we were trying to like explain a discrepancy between the models and the data by saying it's because something really important happens on this 1 kilometer scale.
Okay, thank you, Tom. We've got one final question, and that's about adults who are experiencing fear around mathematics. Is there any one thing that you could suggest?
Yes. God, I could talk about this all night or all day. So I think the thing around fear is or the way I try to combat it is kind of try to make it as relatable as possible to their interests. So again, the kinds of things I've been talking about here of, when I talk to people about, I don't know, let's say adding up points in like a football league table, I'll have people who will tell me they can't do maths, they hate maths, they don't interact with it in any way. And, and I'm like, well, we literally just had a 10-minute conversation about, the average number of goals or the goal to minute ratio of, like Harry Kane, England striker. And it's like, that is maths. That is exactly the kind of thing you have also just told me you completely hate and you're scared of. But at the same time, we've literally just been talking about it for 10 minutes. So I think sometimes just pointing those things out to people, obviously not in like a, I don't want to say, you're not trying to be like aggressive towards them. You're trying to just sort of like build up their confidence and be like, look, you are doing these things in just a different context, like, because they don't associate, let's say, like sports statistics or whatever as maths. So I think sometimes just kind of emphasizing, look, you're working with numbers, you're doing this all the time when you're not realizing it. This is, you just need to present it in a way that makes sense to them, is what I would sort of.
We're going to have to let you go to sleep now, Tom. Thank you so much for being with us at such an hour, and we look forward to hearing more from you.
Yeah, no, it's been great. And if anyone does have anything else, feedback or questions or anything, you can get me on all the social medias at Tom Rocks Maths, and there is a contact form on my website which comes straight to my email. So yeah, I'm more than happy to answer any further questions, or if people just want to have a chat, that's completely fine.
Thank you, Tom.
Cheers.